Okay, let's unpack this. Today, we're diving deep into something truly fascinating. The physical properties of the lunar surface. Specifically, the regolith, or what lots of people just call lunar soil.
Right, the loose stuff on top.
Exactly. You shared a really detailed chapter on this, plus a couple of news items that connect in interesting ways.
Yeah, one on using regolith for solar panels and another on the health risks of the dust.
And that short Korean encyclopedia entry, too, just defining it. So our mission today is really to pull out the key insights, give you a solid grasp of this unique material, and crucially, why it matters for space exploration.
It really does matter. You know, the moon looks kind of static, but that surface layer, the regolith, it's constantly evolving in a way.
How so?
Well, it's the product of billions of years of bombardment. Meteoroids, micrometeoroids. It's all shaped that top layer in ways that are, well, very unlike Earth soils.
Yeah, the chapter really digs into that. It says regolith is this complex mix of crystalline rock bits, mineral fragments.
Yep.
Right, breccia's rock fragments sort of cemented together. And agglutinates. Similar, but stuck with glass from impacts.
Exactly. Impact melts glue tiny fragments together. Plus, you just have bits of glass on their own.
And the chapter stresses that this mix, this recipe, it changes depending on where you are on the moon.
Definitely. Depends on the local bedrock, the history of impacts there.
So understanding those variations isn't just academic, right? It could genuinely affect where we decide to land or build or look for resources.
Oh, absolutely. The composition tells a story about past volcanic activity, the impact history. It's vital geological context. Interpreting the properties depends on knowing that story.
And here's where it gets, well, really interesting for me. This lunar soil is fundamentally different from Earth soil.
Massively different.
The chapter mentions way fewer mineral types, less than 100 compared to thousands here.
Yeah, that's a big one. Much simpler mineralogy.
And all of those impacts have ground the surface down into what it calls a well-graded silty sand.
Meaning a good mix of particle sizes, from coarse down to very fine.
And this makes the thickness and particle size pretty consistent across large areas, apparently.
Which, from an engineering standpoint, is actually helpful in some ways. That limited mineralogy means fewer complex chemical reactions like you get with clays on Earth.
No clays.
No reactive clays. And that well-graded silty sand description, it suggests something that could potentially compact well, be quite stable.
Right. And the chapter highlights three big things missing on the moon that cause issues here. Water, those clay minerals you mentioned, and organic material.
Yeah, none of that.
So because it's simpler, fewer particle types, no air, no water, no organic stuff, the physical properties are apparently more predictable, falling in a narrower range.
Generally, yes. The main things controlling how it behaves are bulk density, relative density, and, of course, temperature.
The lack of water seems huge.
It's a complete game changer. Water affects everything in terrestrial soils: stickiness, swelling, shrinking, how water flows through. Lunar regolith is bone dry, so it behaves differently. More straightforward in some ways, but unique.
And no organic material means no biological breakdown, changing things over time.
Exactly. What you see is pretty much what you get, geologically speaking.
Okay, so the chapter walks through some key physical properties. First up, particle size distribution.
Crucial properties.
Yeah, it affects strength, how much it compresses, even optical and thermal stuff.
Yeah.
Seismic behavior, too. And they measure it using the phi scale, which is logarithmic, based on millimeters.
Right, the FES scale. It just makes it easier to handle the huge range of sizes you find, from sand down to dust, without using tiny decimals or huge numbers.
So most lunar soil samples have a median size between 40 and 130 micrometers.
Yeah.
Average around 70.
So pretty fine overall.
Yeah, about half of it is finer than you can see with the naked eye. But what really jumped out at me was that 10% to 20% is finer than 20 micrometers.
Oh, yes, the ultra-fine component.
That's the stuff that creates this super fine dust that sticks electrostatically to everything.
Yeah.
The chapter calls it a real housekeeping challenge.
It's more than housekeeping, unfortunately. That fine charged dust. It's abrasive, it gets into seals, spacesuit joints, and it's a potential lung hazard for astronauts. We'll come back to that.
Okay, so size is one thing, then there's particle shape.
Also very important.
The chapter says shapes are super variable, from almost round to really angular. But generally, kind of elongated and subangular to angular.
Think sharp, jagged edges, not smoothed down like river pebbles.
Right, because there's no wind or water erosion like on Earth. It's just impact shattering.
Precisely. That angularity is a direct result of how it's formed.
And this elongation means they tend to pack with a preferred orientation, like they might lie flat more often.
They don't just jumble randomly.
Which makes the soil's properties anisotropic, meaning different depending on direction.
Exactly. Like heat might conduct better horizontally through the soil than vertically or vice versa, depending on how those elongated greens line up.
That seems like a big deal for building anything.
It is. You can't assume uniform strength or thermal conductivity. Designs have to account for that potential anisotropy.
And many particles also have irregular reentrant surfaces, like little nooks and crannies.
Yeah, very complex surfaces, not smooth spheres.
And that affects compressibility and strength, too.
Definitely. More surface area for friction, more potential for interlocking between grains.
The chapter gives some numbers for elongation average around 1.31 to 1.39 based on Apollo samples, and aspect ratio mostly 0.4 to 0.7.
So slightly to moderately elongated, confirming the observations?
These shapes, they really are different from particles smoothed by wind and water here.
They are. Those quantitative measures help engineers build better models of how this stuff will actually behave under load. It highlights the unique lunar processes.
Okay, another property, specific surface area, SSA. That's the surface area per unit mass, right?
Yep. How much surface is exposed on the outside of the particles?
For spheres, smaller means higher SSA. Lunar soil is typically around 0.5 square meters per gram.
Which might not sound like much compared to, say, terrestrial clays, which can be huge.
But it's much higher than you'd expect just from the particle size alone.
Exactly, and that points directly back to those irregular reentrant shapes we just talked about.
All those nooks and crannies add up. They even defined a new thing, ESAR equivalent surface area ratio. For lunar soil, it's around 8, meaning 8 times the surface area of smooth spheres of the same size distribution.
That's significant. It tells you just how complex those particle surfaces are. More surface area means more potential for interaction, gas absorption, maybe chemical reactivity.
Interesting. Then there's specific gravity, basically how dense the actual solid particle material is compared to water.
Right, the density of the grain itself, ignoring any pores within it for a moment.
It ranges from 2.3 to over 3.2, with a recommended value of 3.1 for general use.
That range reflects the mix of different minerals, feldspars, pyroxenes, ilmenite, glass. They all have different densities.
And it's complicated because the particles themselves can be porous inside.
Yes, that's a key point, especially the agglutinates, which are basically melted, soil-trapping bubbles. So measuring the true solid density can be tricky. But 3.1 is a good average for many calculations.
Okay, speaking of pores, the chapter mentions 3 kinds of porosity in the soil. Intergranular, the spaces between the particles.
The main void space.
Yeah. Intergranular, those reentrant surfaces, the little nooks on the particles. And subgranular, actual voids sealed inside the particles, like tiny bubbles in glass.
Exactly. Especially in impact glasses and agglutinates.
And intergranular porosity affects the overall bulk density, while intergranular affects both bulk and relative density.
It gets complicated, but thinking about those different pore spaces is crucial for understanding how the regolith behaves. Intergranular porosity controls fluid flow, like if you're trying to extract water ice. The others affect grain strength and density.
Which brings us to bulk density, the mass per unit volume of the whole soil, pores included.
Right, how much a cubic meter of the stuff actually weighs.
And this varies a lot depending on how packed it is. Estimates range from, 0.3 or 0.4 grams per cubic centimeter from remote sensing.
Very fluffy surface layer, potentially.
All the way up to over 2 GC meter in some Apollo core samples.
Much denser, more compacted material deeper down or in specific locations.
Typical average for the top 15 centimeters is maybe 1.5 GC meter, increasing to about 1.66 for the top 60 centimeters.
That increase with depth is expected. The weight of the soil above compacts the layers below. Classic soil mechanics.
So that wide range really shows how variable the surface can be. Loose here, dense there.
Absolutely. Depends on impact history, maybe seismic shaking, lots of factors.
And this leads nicely into relative density, which describes how packed the soil is compared to its loosest and densest possible states.
It's a percentage, 0% for loosest, 100% for densest possible packing.
And it's a crucial factor for geotechnical properties like strength and how much it compresses.
Hugely important. Engineers live and breathe relative density.
What's interesting is that the chapter says in intercrater areas, the relative density increases quickly with depth. Below about 20 centimeters, it's already dense to very dense.
So that cop layer, maybe the top 10, 20 centimeters, could be quite loose and easily disturbed.
Yeah, that makes sense. Needs to be considered for landing gear, foundations.
Definitely. You need to know if you're building on something firm or
Mhm.
something that's going to settle or shift. Higher relative density generally means stronger, less compressible soil.
Okay, let's pivot slightly and connect all this amazing regolith science to those news items. First, the one about using regolith for solar panels.
Right, the ISRU angle in situ resource utilization.
The article highlights that regolith is rich in silicon and oxygen, key ingredients for solar cells.
The most common elements in the regolith, actually. About 45% oxygen, 20-something% silicon by weight.
Which is a massive draw, because launching everything from Earth is incredibly expensive.
And has its own environmental footprint.
Exactly. So ISRU, using what's already there, is central to ESA's sustainability ideas for space. And companies are already looking at tech to process lunar dirt into solar panel parts.
It's a really compelling idea. If you can generate power locally using local materials, it enables so much more ambitious long-term activity on the moon.
The article also mentioned this critical germanium shortage.
Ah, yes. Germanium is used in some very high-efficiency solar cells, especially for space.
And recent export controls have made prices shoot up.
Which makes lunar silicon look even more attractive as an alternative, reducing reliance on fragile Earth-based supply chains for critical space components.
It does seem like a perfect storm almost.
It provides a strong push for developing that lunar silicon technology sooner rather than later.
But the article also has a reality check. Big challenges remain,
Oh, for sure.
especially in developing efficient energy capture and transfer tech that can actually work in the harsh lunar environment. It's one thing to have the raw silicon.
It's another thing entirely to extract it, purify it to solar grade, manufacture cells, connect them, and make sure they survive the temperature swings, the radiation, the dust. Huge engineering hurdles.
Yeah, not trivial. Okay, then the second news piece from NASA focused on health risks from lunar dust.
A very serious concern.
It flags that this dust, with its unique properties, those fine, sharp particles we talked about, could potentially harm astronauts. Respiratory issues, cardiopulmonary, eyes, skin.
And impact their performance, too.
NASA had set exposure limits based on research, but it's a risk that needs careful management, especially on longer missions or if samples are brought into habitats.
This links directly back to that sub-20 micrometer fraction and the electrostatic properties. That dust is nasty stuff to breathe or get in your eyes or lungs.
Its abrasiveness, the potential for lung damage. It's not just like household dust.
Not at all. It's sharp, it hasn't been weathered smooth, and it can have reactive surfaces.
And this brings us right back to the chapter mentioning the fine electrostatically charged dust and the housekeeping challenges.
It's the same problem viewed from different angles. What makes it hard to clean also makes it potentially hazardous to health. Dust mitigation is absolutely critical.
Finding ways to keep it out of habitats, offsuits, out of lungs.
Essential for any sustainable lunar presence.
And finally, that short Korean Wikipedia entry just gave the basic definition. Regolith is loose, mixed stuff covering bedrock.
The general term, yeah.
Used for Earth, Moon, Mars, other places. So while we focus on the Moon's version, it's a wider concept.
Good reminder. Regolith happens on many airless bodies. But, as we've discussed, the specific properties of lunar regolith are unique to the Moon's environment and history.
So, wrapping this part up, what does this all mean for you? Hopefully this deep dive gives you a much clearer picture of lunar regolith, what it is, its key physical traits.
And why those traits matter so much.
Exactly. Whether you're thinking about building habitats, deploying solar arrays, or just keeping astronauts safe, you have to understand this unique lunar soil.
The potential for using it as a resource, ISRU, is huge. It could unlock sustainable exploration.
But we also have to be really clear-eyed about the challenges. That pervasive, clingy, potentially harmful dust.
And the sheer technical difficulty of processing materials in space, turning dirt into functional hardware.
It's a fascinating mix of opportunity and difficulty.
Absolutely. It shows how everything's connected, from the microscopic particle shapes to grand plans for lunar bases and off-world energy.
Here's where it gets really interesting. Reflecting on all this, you see these deep connections, don't you?
You really do.
The very things that make regolith a potential resource, its composition, rich in silicon and oxygen, are tied to the things that make the dust a hazard, its fine, sharp, reactive nature.
And the environment itself, no air, no water, simplifies some things compared to Earth soil.
But it also creates the unique dust characteristics and the soil's overall behavior. Nothing exists in isolation there.
So what does this all mean? I think this exploration into regolith really highlights the complexity, but also the opportunity of using resources beyond Earth.
Yeah, it's definitely not just about grabbing some moon dirt.
Not at all. It demands deep understanding of its properties, figuring out how to actually work with it, and seriously addressing the risks.
Which leads to a final thought, maybe something for you to ponder.
Right.
As we genuinely get closer to having people living and working on the moon for extended periods, how do we strike that balance?
The balance between harnessing the immense potential of lunar resources.
And managing the very real health and environmental considerations, both for the moon itself and potentially anything we bring back to Earth.
That's a huge question.
It really is. And the answer, or answers, will undoubtedly shape how we explore space in the decades ahead.